Just yes, visible. Screen is visible.
Oh, in that case, you are ready to go, sir.
Okay, but wait for 5 minutes, no?
Yes, no problem.
Wait for 5 minutes. So now, just now I have given a message on WhatsApp. So people will join.
Sure, sir. Sure, sure, sure.
Now that is a habit. We have to intimate that okay, everybody is ready. Come. So people start coming. So just wait for 2 4 minutes. Sai Krishna,
Yes, sir.
good morning. We'll go ahead. Okay. So, good morning, participants. Welcome to this day again by the Entuple. We have with us again the team of Entuple, and they will take us through the physical design flow. And today's sessions are like this. Now we will start with the Entuple from 10 to 1 o'clock, 1:15. Then there will be a lunch break. Then 2 o'clock to 4 o'clock, again Entuple. And then finally, you know that we have planned evening session 5 to 7 from the Dr. Prashant Nair. So over to you, Sai Krishna.
Yes, thank you, sir. Very good morning, everyone. Hope I'm audible and clear, and hope everyone joined in and are ready to get through our session. So, yesterday we have actually seen how the ASIC flow, the front initiation of backend starts. So, we have actually been through the full custom IC design, and then coming to the semi-custom IC design. We have actually seen how the architecture is built, how it's split down into microarchitectures or subblocks, and we have also seen how the RTL code is built, how is it simulated in three stages using compilation, elaboration, and simulation. And then we came down to synthesis, which is where the backend starts. And during synthesis, we have seen each of its inputs in detail, what are its content, what is its importance, and how do they actually affect the flow. And through translation, mapping, and optimization, we have done the synthesis on Cadence Genus tool, and you have also seen the timing area and power reports. And when it comes to timing analysis, we have also understood how exactly timing analysis is done, right? So before we actually start today's session, then we'll be starting with the physical design flow, initially covering all the concepts related to it, and then the industry perspective, and adjacent to it would be the demo using Cadence Innova's tool. But before we started for today, any questions or anything from yesterday that is not clear to any one of you? If there are any questions or anything, you can please post them in the chat box. We'll quickly go through them and um, we'll start today's session.
Anybody has any questions? Sai Krishna, yesterday we got major feedback as I told you that your voice is many times is not audible, it's not louder enough. So just make sure that your voice. Can you make louder than what you are talking now? More than that is possible.
Is it okay now, sir?
Yeah, but this position you have to maintain. I don't know what are you doing, but then continuously this much louder has to be there. Otherwise, it becomes very difficult. That was the major feedback yesterday.
Okay, sir. I'll try to maintain this. In case,
Yeah,
yeah, if you,
now it is okay. See, now at this point of time it is okay, but make sure.
I
And
understand, sir.
yeah, yeah, and I request participants also if Sai Krishna is not louder or any problem is there, at that point of time only you uh, unmute yourself and request, or in chat box you write. After the session, there is no point in telling that voice was not audible. So please interrupt, no? Okay. Sai Krishna, that will be fine, right? If somebody requests. Yes, yes.
It's perfectly okay.
Yeah, yeah, yeah.
Let me just tell you this that because of this little cold, maybe low. So if anyone will please unmute yourself. Let me know that so that I can correct my volume and continue ahead.
Yeah, yeah. That's what I want to do. That's it. Otherwise, you go ahead with the session now. Go ahead, sir.
Okay, sir. Fine then. Uh, so as I earlier discussed yesterday in the ASIC design flow, the section of physical design is particularly a five-stage process where we start with floor plan and then continue placement, CTS. So all these five stages are uh, the primary, I mean, framework for your physical design flow, and each stage has its own importance. So today, first we'll be dealing with each of these stages individually. Look at what exactly is happening at each stage, what is its importance, and how is it actually affecting your, chip performance. And we'll go ahead with timing and power sign off, and then the final physical verification. Okay. So the first one comes floor plan. So before I start floor plan, let me just example to correlate the PD flow to you know better. Uh, it's a very common example that is given in the industry. Sup you actually have some land and you want to build a home for yourself. Okay. So what is the step-by-step procedure that you actually follow? First, you will actually check the dimensions of the plot that you have. What is its length? What is its breadth? And what is the total area that you have? Out of that area, how much do you actually want to use for your home? And so you will actually be splitting it up, right? So once you define the dimensions and the area that you have, first you estimate that, and then you go to an architect, get a blueprint, you plan out everything, and then you ship in your raw materials and your machinery to actually start the construction. But here, raw materials can be directly used, but your machinery actually needs a temporary power setup, without which they would not run. So before you actually start your construction work, you get a temporary power supply, and then uh, get to work. Now, as the work goes on, you will be having certain deadlines, right? You'll be planning in such a way that in so and so days the foundation has to be laid. In so and so time period, your walls has to be raised, the slab, etc., etc., etc. So you cannot actually directly control all the work that's going on. So you will call in a person, someone who would be the in charge. So this in charge will actually redirect all the work and make sure everything happens in sync. All the work around the corners of your plot should happen in sync with each other. So there'll be one person who does that. And that way, once all your house is built, you finally go for your wiring, electrical wiring or plumbing or any of that sort of works. And once that is done, you finally check whether everything is proper or not, and then you go for your housewarming, right? So this is what generally happens everywhere. Now, if you closely observe, even your physical design flow very much similar to what I've just told. The PD flow or constructing a chip, constructing a chip's physical design is very much analogous to building a house. So let me just make it more clear. The purpose or the work you do in estimating your plot and margin is nothing but your floor plan, and then setting up a temporary power mesh or some power source, a temporary power source is what you do under power plan, and then getting to work, uh, getting to work and starting to complete things. Uh, I mean, allotting resources, getting things done at each and every point on the workspace is your placement. Calling in an in charge and making sure everything runs in sync is nothing but your clock tree synthesis, your CTS. Y- getting the wiring done is nothing but your routing. Making sure everything is proper and exactly as intended is your physical verification. And then the final aspect is your GDS creation and it out. I hope I hope the example is clear. So let's get into details for each stage. So starting with floor plan, as I said, floor plan basically deals with uh, estimating and marginalizing your workspace. So as yes, so as all of you have already seen a chip, some one or the other, you if you recollect it or observe it closely, you will see a thick border on all the four sides and a small square or rectangular structure in the middle, right? So, and that structure in the middle would contain some, it will contain some rough surface. So, that structure at the center is called your core area. Core, that is your core, and that core plus the border that you see on all the four sides together is called your die. So basically, what happens is when a chip is being fabricated, always uh, yeah when it goes for fabrication, always your design is being fabricated at nano scale level. So the core area that you see is nothing but a combination or a group of layers, and the exterior, the border part that you see is actually another setup which handles your input output signals or any other setup that is additionally given to your chip for better working. Okay, so here, if you observe, this core area is what is where all your standard cells, your physical layers for connection actually taken, and the thick border that I've talked about earlier is your input output setup. Now, a floor plan, what you do is your primary focus would be on the core area. So, along with the gates, we have already seen yesterday during synthesis, we have taken a simple example to show you how RTL code is built, and then we have taken it through synthesis. So in a similar way, you can also synthesize a very complex design, you know, something like your processor or any DTMF design or anything. So generally, what you are using across also include macros. Macros are nothing, they are pre-designed blocks that can be directly used as a part of your design. Okay, something like your memory, PLLs, RAMs, ROMs, etc. These are called macros. So these are blocks which can be directly called into your design and used it, and you can directly use it. So in your core area, sorry, in your floor plan, you first estimate the size of your core and die area. That is the first thing that you do, and then you place your macros certain guidelines which will be discussed later. But just keep this in mind that you'll first place your macros and make sure that out of all the area present in your core area, if you assume this to be 100%, for floor plan you will be using only to 70% of total available area, and only in that 60 to 70% you will be placing your macros. Okay, so once that is done, you will place your IO pins all around your core area, as you can see it here. I hope the IO pins are visible. Okay, so this is what is done in your floor plan. Now, what is the importance of floor plan? The thing is, if you have a macro, if you have a macro in your design, a macro could be having uh, some hundreds of pins or even higher. It depends on what the macro is. But from one block to another block, there are tens or hundreds of pins, and placing the macro is so important that uh, the way you place the macro defines the length between the pins of the macro to that of the standard cells or the gates connected. In physical design, whenever it comes to timing, please do remember one thing, that longer the wires, higher is the resistance, and so higher will be the delay. Because of which the setup of a sequential cell, the setup slack of a sequential cell can be adversely affected. So yesterday we have already talked about setup and hold, and as I told you, setup slack is required time minus arrival time. So here arrival time is nothing but the propagation delay, right? So higher the routing length, higher is the wire delay, and because of propagation delay also increases. That means your setup slack might go towards zero or negative. Okay, so floor plan is important both for your timing as well as it has a direct impact on the quality of your final design, because the way you do your floor plan affects your power planning and placement affects your CTS, clock tree synthesis, and placement and CTS together will affect you during your routing. So each step is interlinked, and so we have to make sure that everything is perfectly in line and clear of any violations. So yeah, so as I was telling, you do floor plan first to arrange the blocks on a chip, which are nothing but your macros, and then your IO pads, or and then you also make sure you do not form any congestion between the cells. Congestions are nothing but too much accumulation of anything is congestion. So if any of your gates, your standard cells, are accumulated at a certain point, then that is called placement congestion. If too many wires are being accumulated at a single point, that is your routing congestion. So both placement and routing congestions actually impact the functionality of your design, because certain wires shall be skipped, and when you don't have that connection, obviously your functionality collapses. So a good floor plan is always important to make sure your design is really good. And in the image you can see how the macros are being placed. This is just an example. We shall look at it more in detail during the demo session. So in order to perform your floor plan, in order to, or in other words, in order to get started with your physical design, the inputs you need are the first thing is your gate level netlist, your block level SDC, and then your Liberty files. Three are your primary inputs that you'd require, and along with this, you might also, uh, chip architect, if he, I mean, from the chip level, when you're dealing with a block, I mean, or let me keep it more simple. There will surely be a difference when you look only at a block and how the pins could be placed to looking at a complete chip and understanding uh, what are the pins of a sub-block that are communicating with another block, right? So when you look at the chip level, you understand that certain pins need to be placed in a certain manner in order to be close to its communicating second sub-block, right? So in such case, your chip architect might actually define the coordinates, the location of your IO pins. So those locations, along with those locations declared for the IO pins are given in the form of IO placement file. So even that is a sort of script which can be directly read, and your IO pins declared in that list shall be directly placed, as you can see it here. This is only an example. So once you read all these inputs, estimate your core area and diarea, and then place your macros and sorry, uh, first use a 60 or 70% of your core area and then place your macros and then your IO pins. Once that is done, you will be ready to place to get your power mesh into the picture, and subsequently also place your standard pins. So uh, the steps of floor plan, the first thing that we were talking about is core utilization. So as I said, we generally take 60 to 70% of the core utilization. Now, what exactly is CU? Why are we starting with 60 to 70%? What happens if we go less or above that? Basically, um, as we have discussed yesterday, if in your with respect to your timing, uh, for any given path, if your slack is negative, that means your data is being lost and your functionality could collapse. Now, in order to in uh, in order to make this timing better, okay, in order timing better, you can add a series of inverters or buffers to boost up your signal. So when you're dealing with a highly complex design, it is it I mean nowadays in the industry, it is a very common practice uh, add these buffers in the data. What I'm about data paths. Okay, the path where the data flows, and I'm not about clock it. So for every data path, you have buffers wherein your timing gets better. Okay, so as we in the industry become a common practice to add these inverter buffers that CTS and routing especially in order to optimize your design, we do that. Now from your synthesis, have a area estimate, right? Yesterday you might seen it in the area report of your synthesis. Let's say you have some x square nanometer. Now, if now we cannot actually determine whether uh, 10 or would be required, or we cannot determine the number of buffers, the type of buffers for that matter that could be added during the next subsequent stages to better your timing. So that is why what we do is we start on an average 50 to 60%. That means out of the available x square micron, area, we take only 50 to 60% dedicated for your floor plan. Okay. So what happens is in this 50 to 60% area or almost 70% area, place all our macros. IO. Okay. Please note, are dealing with simple design, have a restriction uh, to place IO pins at any particular point. IO pin placement can also be done using sorry, can also be done along with standard cell placement. But if you have a restriction to place at so and so cost, then you will be doing IO pin placement along with the floor. Okay, so uh, for placing your macros and your IO, only that 50 your whatever is the core utilization that you mentioned. Here, one important point is there are two types of utilizations. One is standard cell utilization and the other one is core utilization. So as you can see here, core utilization is standard macro area to your total core area. Normally, whatever is your macro and standard cell area, total area will be a little more than that. Okay. So whatever is the fraction you get, its corresponding percentage will be your core utilization. In case if you don't have a macro in your design, then only standard area divided by core will be your standard cell utilization. Okay. So this is one of the three factors that determines that determines the quality of your floor plan. Now, apart from utilization, you also deal with aspect ratio. So aspect ratio, to keep it simple, is the vertical height, the ratio of vertical height is to horizontal width. That means if this is your core area, the vertical height that you have to the horizontal width, the ratio of this height to width is your aspect ratio. So if your aspect ratio is 1, you'll be having equal height to equal width. If it is less than 1, that means your height is less than your width. If your uh, you know if your aspect ratio is greater than 1, then your height is greater than your width. Okay, aspect ratio greater than 1, height is more. If it is less than 1, width is more. So how are you going to define whether you need you have to take a mac aspect ratio less than 1? That depends on the left file that you read as another input. I'm sorry, I think I missed it. You also read your left file as another input for your when you start your physical design. So um, so your left file will contain the list of layers, especially the list of metals that you can use for your routing your design, right? So out of all the metals, starting with metal 1, then 2, 3, 4, metal 5, 6, 8, metal 9, or so until wherever it is, if your metal 1 is given a direction horizontal, then your metal 2 will be given a direction vertical. Alternatively, metal 3 will be horizontal, metal 4 will be vertical, and this pattern continues. So if all your odd number metals are horizontal, all your even number metals will be vertical or vice versa. Okay. So let's assume that we have, let's say, 9 metals. So in this 9 metals, if you assume all the odd number metals given horizontal direction, okay, that means you have 5 horizontal route. That means five metals are used to connect only from left to right, and four metals are used to connect top to bottom. Okay, I uh, hope you are able to imagine it. So we use any connection in a chip design is made only from left to right or top to. You do not take it diagonal or at any angle. Okay, so so right now in our example we have five horizontal routing metals, vertically routing metals. Okay, so when you have five horizontal routing metals, that means you can make more left to right or horizontal connections than top to bottom or vertical connections, because you have more horizontal resources. So when you horizontal resources, they will be stacked, or they'll be made one above the other. So that means you can use more height for your core in order to accommodate a more number of horizontal connections. And on the contrary, if you have more vertical resources, then you can accommodate only from left to right. You can accommodate vertical connections side by side. So that means you need more width. So that is how you define your aspect ratio, whether it should be less than 1 or greater than 1 or equal to 1. Okay. So apart from your core utilization and aspect ratio, there is another uh, factor, which is your core to IO boundary. So that we'll be showing it during the demo. And as you can see, uh, these are a couple of examples to show you uh, the low and high core utilization. Everything that you see here are only standard cells. There are no macros here. So if you have low core utilization, you will see too many gaps in between. Whereas if your core utilization is high, that means you made your floor plan properly, and in the subsequent stages, everything went properly following a certain standard. Then, as you can see, you will see very minimum, uh, very minimum gaps, which means you used your core area very efficiently. Okay. Please do remember that area is of utmost importance, because even if your chip size increases by a fraction of a micron, a fraction of square micron, you will have to be investing some extra amount, which could turn out to be very costly. Okay, so that is why you always intend to use as minimum area as possible, as low power consumption as possible, but the best timing as much as possible. So, uh, so in floor plan, once after you are done with your um, yeah, once you are done with your aspect ratio, utilization, and core to IO boundaries, uh, you then come for IO pin placement. So IO pins could be relating to your signals or relating to your power, or it could be just some dummy cells to fill the gaps that we have seen earlier. So if you already have a IO placement file, you will be directly sourcing it in your EDA tool, so that at the exact precise location, the corresponding IO pin will be placed. If that is not the case, you will have to manually place it as you'll have to manually place it as a part of your floor plan. Or you can, if your design is not too complex, if it is, let's say if you're having a standard cell count of less than 100 or 200, then you can directly use the IO pins along with your standard cell placement. So once your standard cells are placed, the final step in floor plan is your macro placement. So I'll just keep it simple for you. So whenever you're placing macros, there are a set of guidelines that you have to follow. Okay. The first one is that always your macros have to occupy the edges of your core. In a certain conditions where you only have a single macro or etc., as much as possible, you have to stack your macros to get which are of the same hierarchy and place them along your boundary. So let's say I have four memory macros, one PLL, and some two or three miscellaneous macros. Okay. So then what I'll do is I'll take the four memory macros and place them together side by side along any one boundary. And I'll also take the PLL and place it again at any other location. So like this, I'll only first cover all along my boundary. In case if I'm left out with macros and all the boundary is completely covered up, then I'll move inwards towards the center of towards the center of my core. So that way I'll be filling all the macros first. We have to make sure that the first guideline, no macro is left out. Everything should be placed within the core boundary. And second guideline is that all the macros should be along the core boundary. And the third thing is that uh, you should never rotate your macros by you should never rotate your macros by any angle except for 180 or 360. That means you can flip your macro vertically or horizontally, but you cannot rotate them clockwise or anti-clockwise. The reason is because macros themselves are nothing but predefined designs. Even they have routing structures internally. So if you are rotating it by 90 degrees, that means you are changing the direction of the polysilicon or any other metal, or for that matter, every single layer inside that macro, which creates a problem during fabrication. So that is why rotating macros is strictly prohibited, but you can flip them. And another important guideline is that majority, I mean, as I said, every macro could have tens or hundreds of pins. So these pins could be actually being connected to your standard cells or your IO pins. So if they are being if majority of them or all of them are connected to your IO pins, then you have to flip your macro in such a way that they are as close as possible to your IO pins. Whereas if majority of them are being connected to standard cells, then you have to flip them inside. Okay. So these are the basic guidelines that you have to follow. There are still a lot more to add to it, which we'll be showing in the tool demo. Uh, so next, moving on, after you are done with the complete floor plan, all the steps, you then move on to power plan. So here, power plan doesn't mean building up a power source. It's a common misconception that the word power plan induces an idea of building a power source. No, here we are only building a setup, a mesh to propagate or to make sure every cell, every cell or every macro in your design receives power from an external source. Okay. Now, when you're dealing with a sub block in a chip, you will have a separate power block from where through two wires, one for positive and one for negative or ground, will be connected to your subblock, and from there, from that point, your power must be distributed internally to each and every cell. So if you look at the picture here, you can see you have two colored pins on all the four sides. So these are your VDD and VSS pins. You can assume, let's say, for our understanding, the reddish, the reddish shade indicates VDD, and the blue indicates ground. Okay. So as you can see, first there are a couple of wires that run all around your core area, uh, and they are being connected to your VDD and VSS pins. So these two wires that run all around your core area are called power rings. Okay, they are called your power rings, and there are also uh, wires that are running across your core area on top of it. So they are your power strips. Okay, here just to avoid the clumsiness, we have only taken um one set of strips, but normally when you deal with the industrial level designs, we take a group of strips which form a complex mesh. Okay, so this power rings and power strips, sorry, along with the rings and strips, you also create rails uh, for your standard cells, wherein from the complete setup they tap in power and operate. Okay, so all this mesh and all this setup is actually done because if you directly try to give power to each and every cell, because of the increasing complexity of designs or the increasing transistor count on smaller chips, it becomes very bulky, and very complex to do that. And also, nowadays we are using low threshold cells which have high leakage currents, and also the switching happens very quick, especially in the deep submicron technologies. That is, below your 45 nanometer or below your 22 nanometer. So that's why it's important to power plan your design in order to, um, in order to propagate the power properly. So as you can see, this is how your ring is created. The series of horizontal lines that you can see here at the center are your standard cell rows. Okay, they are your standard cell rows, and yeah, they are your standard cell rows, and uh, each standard cell row is equidistant. That means take any two consecutive standard cell rows, the distance between both of them will be exactly the same from top to bottom. Okay, so it is between these two consecutive standard cell rows that a cell, any standard cell, a gate or anything comes and sits down. Okay, uh, if you recollect the full custom flow that was discussed yesterday in the first session, we have created a VDD and VSS rail. Remember that? So that VDD and VSS rail is what is represented here as standard cell rows. Okay, so during your power plan, you first create a ring, and then the strips, and then the rails. Please note that every metal, every metal during fabrication is drawn, or it is framed at a certain height. That means, let's say you take a ground reference, I mean zero level reference, and if you take a zero level reference for polysilicon, above polysilicon at a certain height, your metal 1 is drawn, and above that your metal 2, and above that your metal 3, and that goes on. Okay, it is just like it is just like the parallel corridors in a building, but the only thing is in excuse me, but the only thing is instead of running parallelly in the same direction, here every alternate metal will run in perpendicular directions. Okay, and the gap between them is covered by vias or vias, however you call it. They are covered by vias, which uh, you know which stand like the staircase between two floors for connection. Okay, so so what happens is, because we are doing it for power distribution, we generally want the least resistive path, right? We generally want the least resistive path. What happens if you have high resistance? Your voltage drops and there would not be enough power for your standard cells to operate. So that is why what we do is we always take the top highest available metal layers. That means let's say if I have 11 metals, 1 to 11, I'll use metal 11 and metal 10 for creating my power rings and power strips. Okay, because as the metal number increases, that means from 1, when you go towards the highest metal available, the width keeps on increasing. The width of the metal keeps on increasing. So that means metal 9 or metal level 11 or whichever is the highest has most width compared to metal 1 which has the least. So higher the width means higher the area of cross section. So resistance is equal to resistivity into length by area of cross section. So higher the area of cross section, lower is the resistance. That is why we use the top two metal layers. Okay. So when you create your ring and strips with the top metal layers, and on the other hand, your standard cells, which are initially created from your full custom IC design flow. If you recollect it, yesterday we have drawn the rails from metal 1. The pins and all the pins and rails are made up of metal 1. So you will have to connect this highest metals with which you have made your rings and strips to the least metal 1 with which you are going to create a rail. Okay. So your rail will be all along this standard cell rows. So here what you see is from the top view. Okay, it is from the top view. So because you are looking at from the top, you will see that metal 9 or I mean the highest and the lowest metals will be overlapping. But actually there will be a distance between them. There will be a height gap. So using vias, you will connect them. You will connect your rings and strips to your rails. And when your rail is actually, sorry, when your standard cell is actually placed between two rails, they tap in power. Understood? So this is your ring creation, and you can see the magnified version. You have your VDD and your VSS. Uh, and then this is how your strips are formed, horizontal and vertical strips. So your horizontal strips will connect the edges, the left and right edges of your ring, whereas your vertical strips connect the top and bottom edges of your ring. Okay, this is done to create a mesh and a parallel connection to lower the resistive path further. And so this is the top view. I'm reminding you. So from this, when you actually draw a rail, this is how it looks. So every standard cell row is replaced with a metal one track. So this blue line that you see, dark blue line is your metal one track. Okay. You can see this. I mean, you can identify it with the color and texture from the layer palette here. So I will show that during the demo. So this is how your design would look at the end of your power plant. Okay. Normally, if you already have a VDD and VSS pin declared, then you directly start with your power ring. But if that is not the case, you will actually create two virtual pins of VDD and VSS on the name of Global Net Connect. You will create two virtual pins for VDD and VSS on the name of Global Net Connect, and then do this procedure of creating rings, strips, and then the rails. Okay, so this is your power plan. Now between the two consecutive power strips, one is VDD and the other one is VSS. So between these two rails is where your standard cell would be placed in the next stage. Okay. Imagine the cursor movement to be a standard cell border for a better understanding. Okay. Uh, Also, for your information, every standard cell, no matter what design it is or what gate it is, every standard cell, depending on the technology node, will have the exact precise same height. The height of every standard cell present in a given library will be exactly the same. However, the width can vary. So that is why your standard cell height and standard cell row height are exactly the same, and um, every cell will never cross over any of the standard cell rail after being placed. Okay, so this is the strip view. So you can have a look at it for a moment. So all the spacing and widths shall be explained to you during your demo part. So once all your machinery is ready to get to work, you will have to allot it and start your work, right? So that is done under your placement. So till now, your floor plan and power plan are two stages where you intend to um, where you are actually making a setup. You are getting things ready. Okay, but it is from placement where the efficiency or the quality of your physical design actually can be determined in terms of timing, area, and power. Okay, so please note that floor plan, as you're starting your utilization somewhere between 50 to 70%, as you complete your power plan, uh, let's say, just for our understanding, let's say that you started at 60%. After floor plan, you have come to 65%. Now, during placement, when it is a process, this is the stage where all your standard cells and interconnects are assigned positions within the core area, within the available area. That means your standard cells will use the empty area in the first 65% plus the remaining 35%. Okay. Uh, yeah, the remaining 35%. So, how is this allocation of standard cells and their interconnects done? First of all, on what basis is placement being done? There should be some principle that drives the place, right? Now, along with that, what are the stages that it takes? So, um, so as I already told you, during your floor plan itself, your macros are already placed, right? So these macros will be fixed during your floor plan itself, and so you're not going to move them in any manner. Now, only in the gaps available, you're going to place your standard cells. So these standard cells are nothing but the gates or the components that you have seen in your RTL schematic after synthesis, or the list of components that is present in your gate level netlist. Okay. So we'll discuss more about that during the demo or the later part of the section. So, so yeah, as I said, you'll be calling in your standard cells. But here there are a couple of things that you have to actually take care before you call in your standard cells. Please do remember that all the EDA tools that you use for this process are actually dummy. Your EDA tools only perform calculations, but they do not understand what is a standard cell and what you're doing. Okay, so it is because of this flaw that sometimes when your area is limited but you have more number of standard cells, any a few cells might partially or fully be placed between two standard cell rows, but out of your core boundary. That means let's say that this is a core. Let's say this is the boundary I have, and these are two standard cell rows. Okay, ideally, uh, any standard cell should not cross or should not be placed over the left or right side boundary, because if that happens, that particular cell or the part of that cell whichever is out of the out of the boundary will not be fabricated. Because of that, that particular cell or that group of cells will become dull, and hence again your functionality collapses, your chip application collapses. So that is so but we know that fact, but your EDA tools does not understand it. So that's why what we do is, to the left side and right side boundary, we place certain dummy cells whose job is to block any standard cell that tries to move outside the core boundary. I repeat, as the EDA tool might place any standard cell partially or fully outside the core boundary, which results in not fabricating that part outside the boundary, and hence collapsing of the functionality to the exactly at the boundary, at the exactly at the left and right boundary of your core. We place two dummy cells which acts like blockers. That means they do not allow any standard cell to be placed outside your boundaries. So these dummy cells are actually indications for your EDA tool to understand that uh, this is the end. These cells are the end, and any standard cell that is to be placed must be between these two cells. So there are some physical cells that we use for this purpose, and it's particularly called end cap. End cap is the special or physical cell that is used to block the boundaries. And the other types of physical cells are well tap cells. So well tap is a, I'll keep it simple. Well tap avoids, or well tap acts like a shunt resistance, which uh, which deviates the extra current that is intended to pass through your device or through a gate. What happens when there's a direct short between your VDD and VSS? Heavy current flows through your device, damaging it, right? So to avoid that, you add a shunt resistance in such a way that your gate gets biased and takes in only the required amount of voltage and current, and the remaining excess goes through the shunt resistance to your ground. Okay, so uh, there's the phenomena of directly being short between a VDD and VSS is called latch-up problem. And sorry, when this phenomena happens within a uh, CMOS device, it's called a latch-up problem. And to avoid that, we use well taps. Okay, and then decap cells are, um, as the name itself indicates, decap. They avoid the excess capacitance between, uh, during your between any two components. And then filler cells are just dummy cells to and do not have any functionality, but they just have a material filling. So because of that, there are gaps. Earlier, if you recollect the pictures you saw with utilization, you will see gaps here and there. So to fill them, we use this filler cells. That way, you'll have a poly continuity and the fabrication becomes easy. Okay. And the last one is spare cells. Spare cells are nothing but the unit NOR, uh, which uh, which can be used as a backup. That means if just in case if any of your cell is damaged or anything as such, you can use your spare cells. Okay. So as I already said, this is your well tap. When there is a direct short between your VDD and VSS through your NMOS well bodies, uh, your device might get damaged. So well tap cell acts like a shunt resistance. And then your end caps acts like the blockages at the end of rows. So as you can see here, between two standard cell rows from top to bottom on either side, left and right, your end caps will be placed like this. Okay. And decap cells are your temporary capacitors that are added for your power and ground rails, and these are meant to cope up with the failures because of IR drops, I mean the voltage drops or anything, because now when you have a long net for your power or ground, then basically your power, there will be a certain drop compared to what is being given as input because of the parasitics. So, and also if there is too much switching happening, even because of that, there could be IR drops. So to cope up with it, you use decapsules. And then comes the filler cells, and these are used to fill in the gaps. And then your spare cells, as I said, they're just used as a backup. And the last one is your tie cell. Uh, to keep it simple, these tie cells are nothing but they are direct connections to your VDD or your VSS. So, for example, if you want any of your input or any cell to actually have a direct, I mean, a constant one or a constant zero, in such case, you use tie high and tie low cell. Okay. We'll talk about all this blockages and everything during in the demo. So, yeah. So adding all this, all the, sorry, not all, adding end caps and well taps is what you do just before your placement. Okay. So once you're done with your floor plan and power plan, you add end caps and well taps just before starting your placement. So once you're done with these two, uh, once you add your end caps and well taps, you can now call in all your standard cells to be placed and spread across your core area. So this placement is not a direct, it's not a direct single step procedure. There are certain stages in placement that is followed in order to give you the best efficiency. Okay. So first, so initially a global placement is done, and only then a detailed placement is done. So before we continue, do you need a break, Rathod sir?
Yes, yes.
Okay, then again, how much time is it? 10 minutes or 15 minutes?
10, around 11:30. 11:30 shall we come back?
15 minutes.
Yeah. 10.
Okay, sir. Then let's break for 15 minutes, and once we come back, I'll continue with the Rathod sir.
Yes, sir. We can start.
Sir, in the first session, was the audio okay?
Yeah, yeah, okay.
2 minutes, sir. I'll start. Okay, let's continue. I hope everyone are back. So we were at placement, right? Okay. So as I said, placement actually happens in layers. It happens in stages. So the purpose of a placement stage is to make sure every style is placed onto the core area between two consecutive standard cell rows in such a way that two communicating cells are placed as close as possible. As I earlier mentioned, you are always conscious about the wire length between uh, you're always conscious about the wire length between point A and point B, always, because because you cannot allow longer net lengths, which induces higher delays and thus affect your timing and functionality. So that is why um, so that that is why we always make sure that two, if let's say let us take a AND gate or NAND gate. So it has two input. If you take another two OR gates, assume that the outputs of these OR gates are being given as input to this NAND gate, to an AND gate. So that means if and only if both the OR gates are placed exactly in the same row or just one row up above or below an AND gate, only then the wire length connecting the outputs of NAND gate will be close enough to avoid any extra delay. I repeat, if the outputs of two OR gate been given as inputs to an AND gate, then the distance between or the net length between the to the NAND should be as small as possible. Else, the wire delay increases. That could affect the data propagation at any sequential cell. So, in order to get that very efficiently, your placement stage actually runs in two stages. The first
Sai,
one is
audio again.
global placement, and
Sai, audio. Louder.
okay,
Sai
sir.
Krishna, you can increase your voice a little bit louder.
Is it okay now? Hello,
Little bit you can increase.
hello.
No, Sai.
Hello.
Now okay.
Okay, sir. I'll try to maintain this. Uh, do you want me to repeat it, or can I just continue?
Continue.
Okay. So as I was saying, placement actually happens in two stages. One is global placement, and the other one is detailed placement. So, keeping the purpose or keeping the principle in mind that the two communicating cells should be as close as possible, your tool first runs a estimation on what are all the cells and how are they connected. Your EDA tool will try to run an estimation based on the gate level netlist that you have provided as an input. So based on the connectivity and the list of standard cell gates, and a trial is run first. A placement trial is run, wherein the emphasis is not on whether the cells are placed properly or not, or are they exactly in line with the VDD and VSS, or nothing as such. Not looking for perfection during global placement, but we but during global placement we only just place the cells, uh, you know uh, in a rough manner, and see how close or how better is the timing for various permutations and combinations. Okay, so the permutation and combination which gives you the best result is taken, and then detailed placement happens, wherein every cell is legalized. That means it is placed correctly within its position, respecting its boundaries, and also also proper placement. Sorry, proper spacing between two adjacent cells is given such a way that if there are any pins on the opposite faces of two adjacent cells, there is enough space for the cell for those pins to be routed with metal layers. I hope I made my point clear. Uh, is there anyone who did not understand the placement, how placement happens? Because this is very important to understand how your area timing and power gets affected. Okay, I believe everyone got the point. So, global placement is only a trial, whereas detailed placement is the actual placement stage where your standard cells fit between a VDD and VSS. Okay. So here there are uh, four things that you have to check after your placement is done. The first one you have to check is congestion. So uh, as I said, normally there will be certain space between two adjacent cells whose opposite faces contain pins, but sometimes your EDA tool might miss it. Okay, let's just assume that in a single row you have two cells A and B, and uh, the opposite faces for both the cells contain pins. Let's say some 5 microns is required. Let's just assume that a spacing of 5 microns is required between both of them. Or let me take this example. So here, let's say I need a 5 micron spacing. Okay, here I'm taking the example from the bottommost row. Now, if there are no pins on the opposite faces of both the ends, then they can be abutted. That means they can be placed with zero spacing like this. But if there are no spacing as such, if there is no space, if there are pins, then there should be certain spacing given. If only one of these two spaces contain pin, then maybe 2 or 3 microns could be enough. If both the faces contain pins, then we need more space. So maybe some 5 microns is required. But sometimes what happens is uh, your EDA tool might place these standard cells um, a little closer than required. It might place these two standard cells a little closer than required, which will leave improper or not enough space for all the pins to be routed. Okay, so that calls in your routing congestion. And if sometimes with the intention to abut, that means to place two adjacent cells with zero spacing, your tool might even overlap them. So that becomes your placement congestion. So like this, your placement and routing congestion might happen in high complex designs. Okay, so that is the first thing that you have to check. Normally, congestion, there is a, you know, depending on the EDA toolset that you're using, there is a limit uh, within which even if you have congestion, it's okay. For Cadence EDA tools, your congestion level should be less than 1%. For Synopsys, it should be less than, yeah. For Synopsys, it should be less than 6%. For Mentor Graphics, it should be less than 20%. So like that, uh, every EDA toolset has its own tolerance level. Okay. So if your congestion is within that level, it's fine. Else, you will have to rerun your placement with certain extra efforts. Okay. And once your congestion is cleared, the second thing that you have to check is your uh, area or power or timing. Area and power, you will probably directly get it. Whereas your timing, you will be checking only for setup because till now we do not have a real propagating clock. And so uh, all the clock information for sequential cells is taken only from your SDC. Now, if you remember, our SDC contained clock information also. Create clock hyphen period 2 waveform 01. You were giving certain details, right? What's the time period? What's the pulse width on time? What is the transition maximum, rise time or fall time, etc. So based on that information, an ideal clock, that means instantaneously switching clock, is generated for calculating your timing. That is how during synthesis you got your timing report. Okay. Now even here in your placement, you're going to do the same thing. So that way you check your timing, area and power report. So that is how you check your area, timing, and power report. And then you also check for uh, and along with them, uh, basically your area and power might be almost the same as that of your census report. But when it comes to timing, there may or may not be certain violations. And with respect to timing, there are certain extra factors that you have to also look in physical design. In that, the first factor is high fan out. So HFN or high fan out net is a phenomena where one single uh, cell output drives too many nets. That means this output signal is being given as input to too many cells. So in that case, what happens is your uh, uh, your driver, that means whichever cell is giving out your output signal to be propagated, that cell is called a driver. So these drivers, when they have to face too many fan outs, then it could, you know, it depending on the driving strength of your driver, it may or may not happen. If it happens, well and good. But if it is not able to drive the high fan out, then your data will not be propagated further properly. Okay. So that is a problem that arises with high fan out net. So that's why what we do is we optimize our design, making sure that our fan out reduces in all such cases. And as an alternative, you can also change the size of your cell. That means you can change the driving strength of your cell. You can upsize. That means increase the driving strength or downsize, decrease the driving strength. In either way, your timing might get better, but you will have to compromise on your area and power, because when you're increasing the cell size, the area occupied increases as well as the power consumed. But because you have a higher cell, your signal is pushed faster, and so your setup slack will become more positive. Okay. However, this cell sizing is the last option that we retreat to. Um we'll come back to uh, BT swapping, cloning, buffering, and rebuffering towards the end. So yeah, so after placement, you first check for congestion and then your timing, area, power reports. In case if you have any violation in your timing, you will optimize your design in such a way that uh, you know, in such a way that the violation is fixed and there are no further left out. So yes, this is the congestion I was talking about. So you can see here that wait for pins or cells, there'll be too much accumulation in a unit area, because of which everything might get messed up. So that should be avoided. So after placement, you check all of these and run a optimization, which can be called post placement or pre CTS optimization. Please note this. It is just before CTS, so it could be called pre CTS or post placement. Generally, pre CTS is preferred. So once that is done and your design is clean of everything, you then proceed to clock tree synthesis. So here, uh, first of all, from as the name indicates, you are converting your clock propagation into a tree structure. Clock tree synthesis. Synthesis is conversion, right? So you are just converting a direct point-to-point connection into a tree structure uh, or a split up structure. So, first of all, why do you need this? Why should we go for clock tree synthesis? The thing is, when you have uh, when you have a high complex design, it could actually involve any number of sequential cells. And during your placement, these sequences could be scattered all around your core area. Okay, so that means starting from your clock source pin, the point where your clock starts, the input pin is your source. So starting with your clock source pin, uh, your clock signal must be propagated to each and every sequential cell or a flip-flop which is scattered around your core area, across your core area, sorry, across your core area. So just imagine that there is a flip-flop very close to your clock input pin, and there is a another flip-flop which is very far away. Okay, so now let's say this flip-flop and the one which is very close are communicating with each other. That means they form a edge-to-edge path. Okay, so for one flip-flop, your clock is arriving very early, and so it'll and so compared to the second one, your clock will switch early. But what if, because of this early switching, what if your data from flip-flop 1 reaches flip-flop 2 even before your clock reaching flip-flop 2? It just results in loss of data. Or to simplify it, because of the difference in clock arrivals, because flip-flop 2 is far away, that means the net length is more, and so delay also will be more. So that's why, because of difference in clock arrivals, both the flip-flops might be out of sync. And when they're out of sync, there is a very high probability that your data is being lost. After your first flip-flop launches it, gives out data, your second flip-flop might not capture it. And that results in all your functionality being collapsed. So to avoid that, you have to boost up the clock path. Right now, I'm talking about the clock path. So you have to boost up the clock path from your input pin to the clock pin of your second flip-flop. So for that boosting to happen, you generally add clock inverters or clock buffers. Please note, for clock paths, we are not adding inverters or buffers. We are adding clock inverters or clock buffers. Okay. So that way, starting from your uh, design clock input, you take a clock path, split it up, and wherever required, you add clock inverters and clock buffers so as to make sure that each and every sequential cell in your design receives clock at the same time. Okay, so here receiving clock exactly at the same time is practically impossible. There will be at least a minute difference between all of that. So that is why we try to uh, make sure the clock arrives approximately at the same time. Okay. So uh, when I say approximately, there is a minute difference between clock arrivals. So that difference is called your clock skew. That difference is called clock skew. This should not be uh, confused with clock slew. Okay, this should not be confused with clock slew. Slew, SLEW slew is your transition time. skew is the difference in clock arrivals. Okay, and so that is your clock tree synthesis. Now, when this clock tree is operating, there are a certain factors which we need to be aware of. The first one is clock skew, which I've already explained, and the second one is clock latency. Latency is a synonym for delay. Okay, so clock latency means it is the delay between the source of the clock pin to the flip flops. That means the time taken uh, for your for a clock pulse to start from your clock pin and reach a particular flip flop. Okay, so in this process you can divide the latency into two parts. One is the internal clock latency. That means the delay of a clock to be given out by the PLL, by the phase lock loop. And the second one is the delay that the signal experiences path, all along the path of propagation. So internal latency plus network latency will give you your clock latency. Okay, and yeah, one more thing I forgot to tell you. Uh, Clock inverters, clock buffers are very much different from your regular inverters and buffers. Your regular inverters and buffers will have your PMOS and uh, as all of you know, an inverter is made up of a PMOS and NMOS. So for a given technology node, the length and width of PMOS and NMOS will remain the same in an inverter. And because the buffer is nothing but two inverters in series, the same applies. But the problem is the majority carriers in PMOS are holes and the majority carriers in NMOS are electrons. And as all of you know, holes move slower than electrons. Now, because of this, the time taken to charge or the time taken for the output to switch from 0 to a certain level is much higher than the time taken for the output to discharge from the same high level to 0. I repeat, because of the difference in mobility of holes and electrons, the time difference between 0 to 1 charging or 1 to 0 discharging at the output is different. That means for a regular inverter and buffer, you have different rise time and different fall time. Okay. So now here, if the same applies for a clock, you will when that creates a confusion for your timing analysis, as well as the triggers are given delay or delayed or early. So that's why what we do is in clock inverters especially, you increase the width of PMOS. Excuse me. Yeah, so you increase the width of PMOS uh, between 1 to 2 times. So what happens then is because the PMOS capacity increases, it'll diffuse more holes, when it'll give out more current, and so the time taken for charging your output from 0 to 1 will be shorter. That means your rise time and fall time will be equal when you change the width of your PMOS. So the inverter formed by changing the width of PMOS is your clock inverter, and the buffer formed using two clock inverters is your clock buffer. So for building your clock tree, we are going to use only clock buffers and clock inverters strictly. Okay, and your clock tree is not directly built. There is something called specification, clock tree specification, that is to be mentioned. Clock tree, this clock tree specification contains the information of your clock tree, how and how is it to be built. That means what are the clock inverters, I mean, including the driving strengths. What are the clock inverters or clock buffers uh, that you have to use? What is the name or you know, what is the identification of your clock tree? If you have, there is something called clock gating. So how is that clock gating happening? So all this is given in your clock specification. So based on this clock specification, your clock tree is built. Now, when this clock tree is built, you first check for skew, the difference in clock arrivals. Now, after this is done, you check for insertion delay. So insertion delay is nothing but wherever you need your signal to be boosted up, you're adding some clock inverters or clock buffers, right? So uh, though they are boosting up your signal, they internally provide some propagation delay. So the delay accumulated because of these extra added cells are your insertion delay, ID. Okay. And related to your clock, you will also check your slew, which is your transition from 0 to 1 or 1 to 0. And then jitter is basically associated with your PLL or the source, to keep it generic. Um, Assume you have a PLL that you have designed, and ideally your PLL gives out a clock pulse starting with t is equal to 0, time t is equal to 0. Okay. But when you actually bring it into reality, be it because of the internal parasitics or the temperature around it or any other factor, there will be a very small delay or a small difference. It could be early or late with respect to the point where you expect your clock cycle to start. That means if you're expecting your clock to start at t is equal to 0, it might actually start at 10 picoseconds late, or it might start at 2 picoseconds early, right? So that difference in clock period is called your jitter. Okay. So what is the reason for this clock skew and jitter? It could be because of the network, as we are adding multiple buffers and you're actually connecting it through different wires at different lengths because of the placement of the sequential cells, and also your power supply or temperature could be another factor. Okay. So at the end of the day, all you need is as minimum skew as possible, if possible 0, and also keep the insertion delay low. Along with it, there are some design constraints like your transition, capacitance, and fan out. So this is where your high fan out net comes into picture with your maximum fan out constraint, and what is the maximum capacitance or the load, and this directly influences your transition. So this transition, capacitance, and fan out is common for both clock path as well as your data path. We just have to make sure that in either case or at any point in your design, they are not being violated. Okay. So this is an example of the skew. Uh, let's say So here we have a flip-flop where the total time taken for the clock arrival is 35 nanoseconds, whereas here it's only 5 nanoseconds. So and if both these flip-flops are communicating, then you have a skew, or you have a difference in clock arrival of 30 nanoseconds, which is too huge. Now in case 2, uh, uh, the clock is arriving at 10 nanoseconds for every flip-flop. So that means the skew is 0. Understood? And the time at which your clock is reaching a particular flip-flop is its latency. So that is how your clock tree is built and verified. So this is the source and sync pin, which I've already told you. The clock source is the pin where your clock signal is start. I mean, it starts propagating. So it could be an input port to your design, or output pin of a PLL, or it could be even an output pin of a gate under the concept of clock gating. Whereas the sync pin could be any pin that receives your clock signal. So our primary target is the clock pin that is present inside the flip-flop, or it could also go to a macro, something like your memory cells. So you first create a clock tree spec, load it along with your design, synthesize your clock tree, and then check for uh, your insertion delays, queue, and also your timing reports. So that is all about your uh, clock tree. So what are the impacts of CTS2 placement? Here, some extra buffers are added, utilization increases. There could be congestion, which also has to be checked. And then the last stage in physical design is your routing. So as I earlier said, every metal is placed at a certain height. Every metal is placed at a certain height in perpendicular directions. So the blue line that you see at the bottom most is your metal 1. And then assume there is some metal 2 in between. And then the green line is your metal 3. And then the uh, perpendicular 4. Okay. Like this, each metal is arranged at a certain height, and there will be via connecting fill gaps between both two consecutive metals. This is how of a macro or a gate or IUNs are routed as per their connectivity. Okay,
Sai Krishna,
till
can you please check your voice? It is breaking.
uh, token.
Still, it is breaking. Just check it once.
Hello, hello.
Yeah, yeah, go ahead. Go ahead now.
Is it okay now?
Yeah, yeah. Bit loud, so you
Uh,
can continue.
yeah. Anything you want me to repeat? Hello.
You can
Krishna,
No.
continue
anything you want
further,
me to
no issue.
repeat? Okay then. Fine. So as I was saying, uh, routing is nothing but connecting every pin of it could be your IO pins of the design, or it could be a input output pins of a macro or a standard cell gate. So in any case, so in any case, this routing uses metal layers only horizontally or vertically. So you can see that in the picture that is shown on the slide. So before this routing, in your EDA tools, whatever connections you have, they are only virtual. They are only virtual that are derived from your gate level netlist. But here it is during routing that all the virtual connections are replaced with real physical wires or physical metals. So, um, so the concept is very simple. You'll just replace virtual connections with real wires. But in order for that to happen, there is a lot of background work that is to be done at your routing stage, which fortunately is taken up by the EDA tool itself. So for our understanding, what exactly happens during routing? To understand that, you have to first get to know what are the problems with routing. So first one is the scale. Uh, in the industry level today, as we talk, we generally deal with some tens of millions of standard cells. And if you at least assume, let's say 2 or 3 pins per standard cell, you are actually dealing with close to 100 million or even more pins that are to be routed, that are to be connected. So all of them are to be connected without missing anything. Even if one pin or one connection out of this is missed, your functionality gets affected. Now, along with this, you also have to make sure that with respect to the fabrication point of view, all your wires are in place. That means your fabrication is always based on lines, vertical and horizontal lines. There's a grid, fabrication grid, and all your standard cells or all your routing must be done based on that grid only. So there is a geometric complexity that comes into picture when you have to, that too at nanoscale, when you have to perform your routing. Now, along with these two, you also have to check your electrical rules. Electrical rules means there should not be any opens or shorts, unnecessary opens or shorts, especially uh, especially your data or clock signal should not be connected to any of your power nets. Okay. Yes. So along with all of this, another couple of important points that you have to note is that whatever routing you do, it has to follow your DRC rules. So DRC is design rule check. That means there is certain rules, or there are certain dimensions given in your left file. Actually, that is given by a foundry anyway. But the thing is, those minimum dimensions, the minimum dimensions that your foundry specified must be never violated. That happens, then the connection also would be improper and would affect your data flow and could also lead to bad timing. So that is why your DRCs must be followed. And when you have two parallel nets, uh, when you have two parallel nets side by side, they act like a parallel plates of a capacitor, and a capacitance is formed between both the metal layers. So you have to also make sure that this capacitance does not involve crosstalk of signals or extra delays. The integrity of the signal, SI, signal integrity, should be intact. So when you're dealing with routing, though it is just connecting wires, all these factors must be taken care of. So all of this must be taken care of. So all of that calculation, all of that rule check, everything is done by your EDA tools, fortunately. And yeah, all of it is fortunately done by your tool. But it is important for you to understand how, based on your grid, this routing is happening. Okay. Actually, there is grid-based routing and grid-less routing. Grid-based routing, excuse me. Yeah. So grid-based routing is where you follow your routing grid and make all the connections. So this is, this grid-based routing happens where you have too many stacked, you have too many vertical or horizontal routes that are stacked because of the connections. Okay. So in order to avoid the crosstalk and everything, there is a minimum wire pitch to be maintained, which I shall show you in the next slide. Whereas the gridless routing is more suitable when you want to go for uh, something called non-default routing. So non-default routing is where you generally double or increase your minimum width. Sorry, you increase the width and spacing of the metal layers above the minimum requirement that is given in your left file. So NDR is generally done, or gridless routing based on NDR is done for your clock signals generally, and all your data signals follow your grid based routing. Okay. So as you can see here, uh, these are your grid lines. The horizontal dotted lines you see in the first picture are your grid lines. So uh, the distance the distance between one grid line to the other, where both of them run exactly at the center of your metal layers, is your wire pitch. That is called a pitch. So I don't know how many of you remember, but we'll anyway show it in the demo also. In your left file, you will see the minimum width, the internal width of a metal that is to be followed, the minimum spacing between two um, two metal layers that is to be maintained, and the minimum wire pitch that would be given for every metal. So all of these are taken from your left files. Okay. Now so here we have only taken distance between two grid lines. But in case if you have a VR, there is a separate, you know, there is a separate measurement for that also, and you can see that in the below picture. So there are combinations of line to line distance, line to VR distance, and VR to VR distance. Okay, but one common point for all of them is that your grid line is always the reference, and your metal layer or the VR is, I mean, they, it is tried to place exactly through the center axis. Okay, and as I said, NDR is non-default routing. It is basically used for clock tree, when routing the clock paths to avoid the crosstalks basically. So as you can see here, assuming your signal net 1, signal net 2 and clock are all of the same metal. So this is the minimum width and spacing that are maintained. But when you perform NDR for your clock signals, you see there is more width for your clock, and the spacing between your clock layer and the signal layer is also higher. So when you increase the width of your clock, the overall resistance further decreases, and so clock propagation is better. And having more space between your clock net and signal net will avoid crosstalk. Okay. For your information, uh, crosstalk always happens between two signals. One switches very fast and the other switches slowly. Okay. So here, if you take your signal one, and clock as your reference, your clock switches too fast compared to that of a data signal. Okay. So whenever your clock switches faster than your signal, it will try to dominate the signal that is passing through net 1. So then what happens is, under the influence of your clock, irrespective of the transition that is to actually happen in your signal, uh, yeah, with the influence of clock, irrespective of the actual switching to be happening in your signal, uh, it'll just be following the, it'll just try to catch up with your clock. That means assume that your signal is going down. Okay, your signal in net 1 is switching from 1 to 0, whereas at the same time in your clock it is switching from 0 to 1. So there what happens is, the clock the signal, instead of going from 1 to 0, with the influence of clock, it will again rise up to 1, because your clock is also rising to 1. And so like that, your signal will try to catch up with your clock, which will form a glitch in between, and also could affect your functionality, because you're having a different value uh, up from what you expect. So that is how your crosstalks and happen, and signal integrity be affected. Okay. So to avoid all of that, also we perform NDR. So with all these settings and with all this calculation to happen, your routing happens in 4 stages. First is global routing, where again a trial run is made to find out what is the shortest path uh, for each connection before it makes the actual routings. And then for every routing, be it horizontal or vertical, a routing track is given. This track follows the grid. Okay. So only based on this track, or only in line with this track, overlapping with this track, your routing happens. So initially, your tool is getting an idea on what is the shortest path, and accordingly, it is checking the tracks that is available. So once both of these are done, then your tool goes for detailed routing, where it replaces all your virtual connections in with real physical connections. And once that is done, it will also check for DRC violations. And if there are any DRC violations like minimum width or minimum spacing, etc., your tool will try to clear them off as much as possible. So for this reason, the whole routing is done multiple times in loops. So that is about your routing. So yeah, so after your routing, because you're having physical wires, there could also be a chance of congestion, which is also to be checked. And if the congestion is within the limit, well and good. If not, you'll have to uh, take measures to get it cleared. Okay. this is something I missed. So in your detailed routing, uh, after the shortest path is estimated in your global routing, and tracks are assigned, your tool does not route your complete design at once. It will split down your core area into certain boxes, to routing boxes, and will route one box after another. Okay, so the small areas are called a switch box, and a group of switch boxes are called global routing cells or G. Okay, so first your first route, the detailed routing happens at a switch box, and a group of switch boxes are routed, and that completes one G cell. And a group of G cells will give you a detailed route box. So like that, starting with the most basic structure, your routing goes on happening at every level. And finally, a complete check is done to see if any, if any connection is left out or improperly connected or so. So, uh, as a part of detailed routing and search and repair, these are the aspects that are actually checked: the spacing, the notches, or any opens and shorts. Okay, so that completes your physical design. So, any questions till this point from anyone? Any questions till this point from anyone? Anything that you did not understand? So, shall I take it to be clear? Because I know this is a lot of information, and if there are anyone who is learning it afraid, it might be a little confusing for you. It requires practice. Is there anything that anyone want to repeat or anything?
No,
Okay, I
sorry,
take
I
that.
don't. I, yeah, I
Hmm,
don't think so
yes,
because what happens is if there is a practice if we are doing, then only actually those doubts comes physical placement. No. Otherwise,
I'm
theory
talking
is
about the
okay.
concepts.
Continue.
Yeah.
Yeah, yeah, concepts is
Okay
okay.
then.
I think so. Yeah,
Okay then. So
yeah, yeah.
I'll in the next 15-20 minutes, I'll also quickly finish off uh, an overview of the physical verification and power sign off. Yesterday we have already completed the timing, the timing analysis and the measures that we can take, uh, to fix violations. I'll also talk about that. So if you remember yesterday for timing analysis, especially the post layout timing analysis, to be precise, because our layout is ready. Once your PD is done, that is nothing but your layout. So, so for your post layout timing analysis, along with your design, your liberty file, your constraints, there is an additional set of inputs that you give for STA to happen, and that is your SPEF and SDF, right? SPEF. SPEF is for Standard Parasitic Exchange Format, whereas SDF stands for Standard Delay Format. So after your routing is done, using Cadence Innovers, you can actually, uh, write out the parasitic information, a detailed parasitic information into into any file with the extension of .spef. So this file is going to be used uh, for all the parasitic related analysis or information. So this PEF is written in an IEEE format and contains the parasitic information in ASCII format. So it is readable, but it is really tough to map all the parasitic information back to your design. Okay, so that is where your EDA tool would come into picture. So this is a snapshot of from your SPEF file. So initially in the beginning, you can see the basic information of what is the tool, the units of your time, current, resistance, and and what are the modules or what are the important blocks, and then the ports that you have, and then every port or for every pin, what is the parasitic information that you have. So that is a four parts of your SPEF file. So using this SPEF file, you go ahead and first check your timing. One thing I forgot to mention is that um, after floor plan and power plan, you do placement, check your timing, area, and power. If there are any violations in your timing, then you optimize the design and again check for your timing, area, power violations. Only if they are clear, you go to CTS. And post CTS, after CTS, you again check for timing, area, power, and any violation you perform post CTS optimization. After placement, it is pre CTS optimization, and after CTS, it is post CTS op. Similarly, for routing, after routing is done, you do post route optimization. Okay. So after all of that is done and you do not have any timing violations, then you perform timing analysis to check for both setup and hold. For placement, timing is limited only for setup, whereas for CTS, post CTS and post route, you check it for both setup and hold. Okay, so I believe all of you clearly understand what is setup slack and what is hold slack. So I'll skip that. And as I was emphasizing on what is data, what is clock path. So here is an example. So the path which controls. So data path doesn't literally mean the path in which the data flows, but the path uh, the path that is formed with propagation delay arcs. Okay. So here, as we have discussed yesterday, for a sequential cell, the cell delay arc will be from clock to Q, right? So the first delay arc will be if you consider this to be a edge to edge path. So the first delay will be from clock to Q, and then from Q there will be a wire delay to a wire uh, a wire delay arc from Q to A, and then a cell delay arc for B1 from A to Y, and then again a wire delay, and the delay across all of this will give you your propagation delay. Okay, so that would be your arrival time. Whereas the path where your clock is actually propagating, that means from clock source pin to directly the sync pin or the clock source pin. uh, Initially there's a wire delay and then there is a buffer, so the cell delay of buffer B2, and then again the wire delay. So the delay across all of these arcs will give you your clock path delay and hence the clock arrival time. Okay, so that is why if you mix up both of them, you cannot perform your timing analysis or even if you do, it will not be accurate. So that is why it is important to identify the data path and the clock path. Okay. So setup slack is required time minus arrival time. So the point of time where uh, no, where your data can arrive at, sorry, the point of time or the limit in the limit, the point of time where your data can arrive on or before, minus the point of time where actually your data is coming up. So if your data is arriving within the limit, you will have a positive value. If not, you will have a negative value. If it is exactly coinciding, the slack is 0. So if you have a negative slack, it means your data is arriving late, because of which it could be lost. Whereas when it comes to hold, it is just the mirror image. Here it is setup slack, it is required time minus arrival time. Here it is arrival minus required, or for better understanding, it is launch time minus required time. So after being captured, if your data has to be held stable for let's say 10 picoseconds, and it is actually being sent out at 12 pico, it is 12, launching time 12 minus required time 10. So it's a positive slack. That means your hold is not violated. But if it needs to be held stable for 10 picoseconds, but is being launched at 8, then you have a negative hold slack. Even then, your data will not be handled properly and so could be lost. So in case you have a negative slack for setup or hold, how could you actually fix it? So first, let's talk about setup. As I earlier told you, you can actually upsize or downsize your cell. That means you are changing the driving strength of your cell, which will affect your time, right? So for setup, it is required time minus arrival time. That means to move your slack towards positive, you have to reduce your arrival time. That means you have to push your data faster. That means you need larger cells. So that's why you upsize the cell to fix your setup. Or you add buffers. I mean, you add a buffer of considerable driving strength. You do not add smaller buffers again and again, because that will increase the propagation. Okay. In case if there are any buffers, smaller buffers added repeatedly, you remove them and add one single buffer. Okay. So apart from these two, there is something called VT swapping. VT in simple, VT stands for voltage threshold. Okay. Now, because we are dealing with semiconductors, all of you know that there is a certain threshold that is to be uh, crossed over in order to switch from off to on or on to off. So, based on this threshold, we have three categories of cells: LVT, low voltage threshold; SVT, or RVT, which stands for standard voltage threshold or regular voltage threshold; and the third one is HVT. HVT stands for high voltage threshold. Now, what happens is when you use more number of LVTs, low voltage threshold cells, they switch faster. They switch faster. So that means when they switch faster, that the cell delay reduces, because of which your setup slack could be benefited. But the drawback for that is your leakage power will increase. Okay, LVTs has the highest leakage power compared to SVT, or relatively even lower when compared to HVT. all of these are you know the methods that you can implement to fix setup. Now when it comes to hold, it is just the reverse. That means to fix hold violations, you will have to downsize the cell. That means uh, reduce the strength of the signal propagation so that your flip flop can capture it and then comfortably take it up. Okay, let's take the example of a cricket. So in cricket, if a fielder has enough time and the ball isn't and the ball doesn't require quick reflexes, he can comfortably take the catch. But if the ball comes too fast and he do not have enough time, he cannot take it, right? The same happens here also. The flip flops, if they have to capture your data uh, for setup, because it has to arrive quicker, you're pushing it harder. But for hold, you have to slow it down. And when it comes to VT swapping, you need high standard or higher voltage thresholds, because quicker switching means the next data will be taken in easily, because of which the current data may not be handled properly. So to just keep it simple, if you try to improve your setup, it will degrade your hold. And if you try to benefit your setup, it will affect your, sorry, if you try to benefit your hold, it will affect your setup. So it is like a two-way sword, which you have to balance at both the ends. So too much fixing of setup and too much fixing of hold is not recommended. Okay. So this is the timing report of setup before fixing. So here you can see that slack time is minus 0.06 nanoseconds. Whereas after fixing, this could be, let me make it clear, this could be either through optimization of your design during physical design, or there is something called engineering change order, ECO, which generally comes into picture only after routing. In spite of optimizing your design multiple times, or in spite of doing everything you could, if the violation still exists, then you can go for ECO, engineering change order, where you can implement the aforesaid uh, timing fixes for setup and hold that we just discussed. Okay, so either way, be it optimization or ECO, before setup, before fixing setup, you have your slack time to be minus 0.06 nanoseconds, and after fixing it, you'll have it to be 0 or positive. Okay, and the same applies for hold also. If your slack is negative, here in this example, your hold slack is minus 0.1 nanosecond, which is 100 picoseconds, and after fixing, it goes to positive. Okay, so it is the engineer's responsibility. It is a physical design engineer's responsibility to actually uh, debug the issue. I mean, go through the table, identify the highest delay point, or keep it simple, the point where the timing problem arises, and then take the necessary step accordingly. So along with your so once your timing is done, you also need to check for your power. Generally, in synthesis, you have only seen the numbers for power in your census report or even in your physical design. you only check for the numbers. But power analysis is a complete, different branch which uh, looks into far more fetching concepts than just what is power dissipated. Okay, so today we are going to discuss about IR drops, electron migration, and uh, chip closure. Okay, so the cadence tools that we use for power analysis is cadence voltus, which is one of the industry standard tools after ANSYS Red Hawk. So the first one is IR drop. So IR drop in simple is nothing but drop in your voltage or fluctuation in your voltage at any given standard cell. So once you place your design and route it up, we we I mean in our power planning we were actually supplying all this power through a mesh, and this mesh connected down to a rail, a series of rails. Now at any point on the rail or at any VD or VSS for a given standard cell, there could be some voltage fluctuation because of the parasitics or any other factor. So uh, that phenomena is, to keep it simple, that phenomena is your IR drop. So here you will be, the either the voltage or its corresponding current will go down. Okay. So here at the below picture you can see that the voltage drop, from a device depends on the load, and uh, you know uh, as the load increases, then the switching current also will increase, and because of that there could be a drop in power, which uh, which could cause some dysfunction in any of your standard cell. So uh, here you can see that the actual voltage keeps on changing or fluctuating, but we have uh, a level which is acceptable for proper functioning of any standard cell. So if we say that our standard cells are working at zero point 0.9 volts, for example, so your ideal voltage level will be zero point 0.9. But in the practical scenario, because of the parasitics and the propagation losses, your voltage might be somewhere like 0.88, 0.85, or 0.82 at most, maximum, something like that. So this, uh, though there's a difference in the expected and the actual voltage, uh, that does not affect your that does not affect the working of your standard cells, unless that voltage drop goes below the tolerance level. Okay. Now that means, for example, if you consider time on your x-axis and voltage on your y-axis, uh, the point I'm showing on the cursor from, assume this to be point A and point B, point C and point D. So with respect to time between A to B and C to D, your voltage is dropping below minimum tolerance level, which will make the corresponding standard cell, it'll your standard cell will stop working or will dysfunction. So IR drop analysis is very much helpful to actually eliminate such occurrences and carefully understand or carefully check whether everything is happening properly or not. So this IR drop analysis is done using it's done in two types. The first one is static IR drop analysis, and the second one is dynamic. So static IR drop means You just check, point to point. It doesn't matter whether the power or the corresponding current is flowing from point A to B or B to A. Whereas in your dynamic IR drop analysis, it is vector based. It is vector based. That means every switching and every direction of the flow matters. So we'll learn more about this in the demo. So dynamic, and when you perform this IR analysis, it is not only for your data or your clock propagation. Sorry, excuse me. Yeah. Um, so when you perform IR drop analysis, it is not only about your power mesh or your connections, the routed connections. You also, I mean, there are a certain special set of cells that are induced particularly to check this, to keep a check on your power usage. So that is where your concept of single domain power analysis or multiple domain power analysis comes into picture. And if you have any multiple domain powers in your design, that means one block operating at one voltage, another block operating at another. Such case, you will be using special cells like isolation cells, retention cells, power switches, and level shifters, etc. And clock gating is also done to to many of the synchronous circuits which use clock to save power. Clock gating in simple is nothing but using a combinational cell, something like an AND gate, when the enable is off. That means when clock is not required, you switch off the enable, so clock does not propagate. And so all that switching power or the static power is saved. Only when it is used, enable is given one, and so your clock moves forward. That is your clock gating. Okay. So when you use multi-domain, when you actually perform analysis on a particular power domain, you also check what is the distribution of voltage thresholds you use. Because as I said, you have LVT, SVT, and HVT, and each one of them have their own um, uh, advantages and disadvantages. So that is a brief introduction on your IR analysis. Now the next one is electromigration. So um, to explain it simple, your electromigration is a phenomena where when you in a metal layer, when a metal is conducting current, there'll be some ion displacement, right? There'll be charge and ion displacement. So over a period of time, uh, all this the over a period of time at a certain location on the metal or the conductor, it gets depleted of any ions, and so charges cannot be moving up. So because of that, there will be a bottleneck of charges at that point, which will lead to electrical breakdown of that conductor. So this phenomena is called your electromigration. Okay. So this happens when the current is too high or the same conductor is being used over a long period of time, etc. So what happens is when when at a point it gets depleted of charges or ions, the resistance becomes too high, and it may burst into opens or shorts. So that is why it is the responsibility of the foundry unit to make sure uh, that whatever metals they are using do not undergo electromigration in a very short span of time. Even in our day-to-day life, any electronic gadget, something like your motherboard or anything, when you use it over years, it breaks down, right? That that could be because of electromigration. Okay. So how can we, when the from the design end, the foundry will anyway define the current limits and it and what are all the other factors it does. But on the design end, on the physical design end, is there anything that we could do to avoid this electron migration? The answer is yes. So the first and mostly used technique is to widen your wire to reduce your current density. That is nothing but your uh, non-default routing type. And then if you use lower input voltage, the corresponding current also will be less. So electron migration may not happen. And if you put your wire length shorter length means shorter time your conductor is being exposed to currents, and so even that can help and reduce the frequency. Normally, if you have high clock frequency or high data switching, even then there is a abrupt. I mean, at a nanoscale, it's fine, but when you look at from your perspective, there is a very abrupt change in electron density, the charge density or the current density. Even that could affect the conductor. So once you are done with electromigration and IR drop analysis, and they are clean from any violations or from any problems, you then finally come to the last stage of the complete ASIC design flow, which is your physical verification. So in physical verification, the inputs that you read is nothing but your layout, be it in terms of GDS or be it in terms of any other supporting format. Now, along with your design, you also read in your rule files, just the way you do in your full custom flow. Here also you will have certain rule files, and based on your design and rule set, you perform DRC and LVS. So here, along with in your ASIC design flow, because you are dealing with a very complex design, DRC along with DRC and LVS, there are a few extra checks that you do. They are your ERC, electrical rule check, where opens, shorts, or something like direct connections between VD and VSS, all that is checked. Same in your full custom flow, when you are actually simulating your schematic, this is done by default. But here we did not simulate the physical layout. That is why we check the electrical rule check separately, and then your antenna checks and DFM. We shall see what they are. First comes your DRC, as you all know. We check our design against every rule given by your foundry to make sure your design is fabricatable. So the tool that we use for physical verification is PVS. Earlier, it used to be Ashura, and now it is slowly being integrated into PVS. Right now, this moment, PVS is used for lower technology nodes, and Ashura is used for higher technology nodes. So, what are all checked under DRC? You can see there is the minimum spacing, minimum length. Uh, if it is for via the minimum enclosed area, and are any via stacked above the limit, minimum net spacing, etc. So this is the general DRC where You can see that the minimum enclosure for a via, what the between two nets or between two layers, be it in any form, what is the space that is happening, and if a via has to be put down between two layers, there should be a minimum overlap between the two layers. So even that is checked, and then so all that so all the rules as such are taken into consideration and checked across your design. So there's the minimum width, which I believe all of you would have understood from the full custom flow. Then the minimum spacing between two layers. The minimum enclosure rule defines the minimum area, uh, the minimum area for a via where it has to make contact. So if that contact is not made, then the connection between both the layers, higher and lower layer, also will not be proper. And then end of line spacing is something like your minimum width only. But here, instead of running parallel, they run perpendicular, but do not be in touch. Minimum area requirement is applies for both vias and metals. And if any via is misaligned, that means during your routing, your tool might place your via out of your coordinate, out of track. So even that misalignment is checked. So these are some, this is a sample report. Is very much analogous to your full custom Ashura DRC. And similarly, your LVS is layout versus schematic. So this is to make sure that the layout is properly connected everywhere, because even one wrong connection could lead to a whole different functionality. So you basically check for opens, shorts, or any mismatches in connections or devices. So this is an open, as you can see here. Both of these horizontal metals are to be connected, but are left floating. And shorts is where you use, um, and by any chance, if two, uh, let's say one vertical and one horizontal metal are drawn using the same layer, even then a short can happen. Actually, this is the reason why every alternate metal is given horizontal or vertical direction. And and the next one is electrical rule check. As you all know, it checks for any open or unconnected pins or nets, any dangling wires, or connectivity loops, or any shorts between VDD and VSS, etc. And the last one is DFM, designed for manufacturability. To keep it simple, DFM is a trade-off between the yield and area increase. That means uh, now whatever design you make, when it is clear of all the physical verification, you send it for tape out, right? Now, when you are actually sending it for tape out, your design occupies a certain area. I mean, it'll have a certain die area, and so for a unit silicon wafer, how many are you actually being able to? How many chips are you, productive chips are you able to take out? There'll be, there'll surely be a wastage, but how many chips are you able to take out is what you consider to be your yield. So if in case if your die area is uh, okay, let's not go deep into it. In case if your die area uh, is not giving you proper yield, you may increase, cannot decrease anyway. So you will increase your area using filler cells, and follow certain rules, make sure everything is in line, and get your chip fabricated. So all these techniques are used as a part of DFM, and then comes the antenna effect. To keep it simple, antenna effect comes into picture where you actually it is very similar to electron migration, but electron migration happens within a metal, right? Here, it's a here we take it at the juncture of two metals. Okay, so what happens is, in order to comfortably carry charges or signals from any standard cell to another cell, it has to pass through a certain vias and metals, right? So there is a ratio called antenna ratio, which is area of the metal at the connection point, the area of metal at the connection point divided by the area of gate at the node. So this ratio is mostly less than 1, but whatever is the ratio minimum and maximum range given during your routing, it has to be maintained. Else your charges gets bottlenecked, and so your signal also gets damped out. So in case if there is any antenna violation, that means the ratio is not maintained, then you can these are the three methods where you can rectify it. The first one is adding a buffer so that it gets boosted up. Second one is adding a diode, so that provides the switching and the biasing. And then adding a jumper is like you cut down the metal that carries your signal, you cut it down in between, and you step up higher, you take a higher metal and connect it at either ends. So what happens is here the overall area that is being under contact will increase. So that way your antenna ratio is also satisfied. And the last one is the engineering change order, which I've already talked about. It is the manual effort that an engineer puts in to rectify the errors or the any violations that are being unable to that are being not resolved by your tool by its default algorithms. So that is all about your physical design, timing analysis, power analysis, physical verification, and yeah, physical. So any questions till this point from anyone? I hope everything that we spoke till now is clear. Okay, so just a quick recap from whatever we are today. I mean, just to reconstruct the complete ASIC design flow. First, you start with a specification for your chip, and then a chip architect will break it down into subblocks with a specification for each. Then you take the specification of your subblock and then start using Verilog or VHDL to write a RTL code, a register transfer language code, and that contains all the virtual logic, the functionality of your design as per the specification. So in order to make sure that you are in line with the requirement, you write a test bench or manually using a EDA tool you force certain values onto it, onto your main code, and you force it onto your main code, and then um, you simulate it. So once you simulate it, if for a given input you're getting the expected output, well and good. Else there is some issue with your functionality, so you have to go back and debug your RTL code. Okay, and once the simulation is successful, you then come down to synthesis, which requires three inputs. One is your RTL code, which you have written. The other one is SDC, which depending on your specification and design requirement, uh, you develop it. And the third one is your Liberty file. So your Liberty file contains all the sub-design information that are extracted and characterized from your subdesigns that are made from full custom IC design flow. So through translation, mapping, and optimization, your synthesis is done, and you'll have a gate level circuit whose connectivity is recorded in the form of a netlist, and even your SDC is changed to block level. So gate level netlist, block level SDC, Liberty files, and your left files. Using all the four of these, we proceed to physical design, where you first start with floor plan. You'll check aspect ratio, utilization. If you have macros, you will go for core utilization. If not, you will go for standard cell utilization. And yes, even boundary, the boundary spacing between core and IO. So once that is done, you will first place your macros and IO pins, and then go for power planning, where if you are already given a standard cell, sorry, if you're already given a IO placement file, well and good, because you already have a VDD and VSS also. In case you don't have that, then um, yeah, then uh, you will first create a global net connect, which is just a virtual pins of VD and VSS for the tool to understand. And then you first create a power ring with VDD and VSS, then power strips with the same horizontal and vertical. And then you'll finally create rails. You'll stack all the vias available to connect your highest metals uh, present in the rings and strips to the metal one rail. And after that, yeah, so once that is done, you will then proceed with placement. So placement runs first in global placement stage, where a trial run is done, and then based on the connectivity, a detailed routing is done. So here you have to check for your congestion, timing, area, and power. After that, if there are any violations, you um, you optimize your design once, which is your pre-CTS optimization, and then again check for congestion, timing, area, power. After that, you come to CTS, which is meant to make sure all the clock reaches all the sequential cells approximately at the same time. So you will be using only clock buffers and clock inverters. Build a clock tree spec, and accordingly build your actual clock tree. So once clock tree is built, you will check for congestion, timing, area, power. This time timing will be for both setup and hold, and then any violation post CTS optimization. Once everything is clear, you will come to routing. So after routing is done, again timing, area, power, congestion. If there are violation, post route optimization. So only when all the violations are cleared, you are free to go to timing and power sign off. So in timing uh, sign off, we perform static timing analysis, and if there are any violations found there, in the presence of parasitics, we have certain techniques like adding or removing buffers, increasing or sizing or downsizing cells, adding or removing redundant buffers for setup based on what you're treating, setup or hold. And then you'll check for IR drop, static and dynamic, and electro migration in your power analysis and sort it out. And then you go for physical verification, where you perform DRC, LVS, ERC, etc. And after you rectify your physical verification, you will once again check your timing and power analysis. Only if new uh, no new violation is induced, you will create a GDS file of the design and send it for fabrication. One thing I missed is that the just to confirm your synthesis netlist, whether it carries the exact functionality or not, you perform logic equivalence check using cadence conformal between the gate level netlist from synthesis and the RTL code. Similarly, after routing, you will perform logic equivalence check LEC again between your routed netlist and your synthesis netlist. So only when all of this is done, you will send your chip for fabrication. So this is the effort that is put behind creating a chip which is integrated into a system, and that system becomes your electronic gadget.
So thank you, Sai. Shall we break for the lunch?
Just 1 minute, sir. There is a question here.
Achha, okay.
Let me just answer that and we'll break.
Yeah.
Are there any limitations on physical design? Vadin sir, I think I did not get your question. Can you please unmute yourself and make it clear? Hello, Vadin sir.
Hello, sir. Sir, will there be any unsolvable violations? Have you come across any unsolvable violations?
Ma'am, generally, if you are using a manufacturer grade PDK, there won't be any unsolvable violations.
Okay, sir.
If there are any, then we'll anyway come back to the basics of the specification and everything. We'll make slight changes there and repeat all the process. In any
Actually,
percent, there will not be anything.
1 minute to interrupt, Sai Krishna. Usually, PD process and even timing sign-offs, power sign-offs, all these things will take place in an iterative process, ma'am. Usually, we were not fixing the violations in one iteration or one step itself. So we will be keep on coming, like keep on. We were fixing the violations until it got fixing. So we will be taking 2 iterations, 3 iterations based on the violations we were getting. So usually we can able to fix the violations at the end.
Okay, ma'am.
So it is not like we will be having any limitations to fix the violations or like that.
Okay, ma'am. Thank you.
Any other question? No question. So now, Sai Krishna, shall we break? Hello?
Hello?
Sai, shall we break?
Yes, sir. We can break for lunch, come back at 2 o'clock, where we'll be starting the demo session.
Okay. Saraswati will take, no? I think so.
Yes, sir.
Yes, sir. I will be continuing, sir.
Okay. Thank you very much. So, break for lunch. Please come back at 2 o'clock. So, I'll close this meeting. We'll have a new meeting. starting.
Okay, sir, sure.